reliability in measurement systems, and the idea here is to try to predict how long our system will work and how reliable it is, and even how unreliable it is. And of course, again, it's not only for measurement systems, it's for all kind of industrial systems. And it's an attempt to understand and work around Murphy's Law. Murphy's Law is about how things that can go wrong will go wrong. And there's a story to that figure over here about how NASA experienced the Murphy's Law and about how things really can go wrong, which we will take in the classroom. Failure rate. Failure rate is the number of failures per time unit. So you can, for example, have a failure rate of five failures per year or something. And the failure rate is defined as lambda, and the bar over the lambda sign is that it shows that it's a mean. So it's an average or mean. The failure rate, the failure rate can be defined as the total number of failures within an item population over the total time experienced by that population. And here we have an example of 5 light bulbs, and if we're trying to find the lambda mean for that one, it would be the total number of failures. We had 4 failures, and the total time monitored would be 422 plus 744 plus 803 plus 678 plus 1000. So that would be the amount of hours of experience we had with that light bulb, which cost 4 hours. So the failure rate would be so and so many failures per hour, or failures per year, or even failures per week or something. So in this case, that would be 1.1 times 10 to the minus 3 failures per hour. We could, of course, convert that to failures per year, for example. Reliability is how reliable a system is, and unreliability, how unreliable it is. And as it says here in the text, reliability is the probability that a system will operate to an agreed level of performance for a specified period. So you see here, the reliability goes down as time goes by. So if I have, for example, a light bulb, as in the previous example, the probability when I start the light bulb that it works, it's reliable, it's 100%. Provided, of course, that it wasn't dead on arrival. After some time, we have the reliability of 50%. So after some time, about 50% of the light bulbs work. Well, the rest of them are then unreliable or failed. F for failed. As time goes by even more, at some time we have 25% reliability, so which means that only 25% have survived, and then 75% have failed. So the failure rate goes to 100% or 1.0 blank as time goes by, while the reliability goes to 0 as the time goes by. And the sum of the two is always 100%, or 1. Example here. For a population of 10 sensors, if they've been tested in the laboratory, the survival time is given here, right? So from that I can calculate the failure rate. The failure rate would be that I have 10 failures over the sum of days. So that would be my lambda mean. the probability that a sensor from this population will survive for at least a year, well, then we have to figure out how many days there are in a year, and then we would have to also figure out the reliability R, because it's we are trying to figure out if it's reliable. So the R of t is e to the minus lambda times t. That was the equation from the previous page. And the reliability of it working for 365 days would be about 3.7%. You see here that all the sensors that I have here worked for less than a year, so it's rather improbable that it will work for a whole year. But still, there is a minor probability that it will. Actually, this is not quite correct, because every fourth year we have a leap year, so the average year is 365.25 days actually. What's the probability that such a sensor from this population will fail during 6 months of operation, half a year? Well, you see from this table, most of them did not survive, and none of them actually survived for half a year. Well, this one did. This one survived for more than half a year. But the probability, I guess, it's much less than 50% that it will work. And then the probability that it will fail during half a year is more than 50%. So let's see how to calculate that. The F is 1 minus R. So it's 1 minus 9.03 times 10 to the power of minus 3 multiplied by half a year, which is 365 divided by 2 days. So it's 81%. So it's 81% chance that it will fail during 6 months. More than 50% as mentioned earlier. The instantaneous failure rate is where you also include the early failures and the wear-out failures. So the failure rate, the mean failure rate that we talked about in the previous slides, is actually in this section here, where the failure rate doesn't change very much. For most systems, you have a so-called bathtub curve of the failure rates. You have many failures in the beginning of the lifetime of the product, and then you have many wear-out failures at the end. So say, for example, for a normal car, you would have a few problems in the beginning when it's brand new, and then you would have a rather constant failure rate in what is called the useful lifespan of the system, and then you will have a rising failure rate because of wear and aging of the device, or the device elements. So you have here the dominant the errors could be design errors, weak components, operator errors, and so on. And then you have your useful life here. So for critical systems, like for example a valve in a subsea control system in or a subsea valve system in a petroleum business, then you would actually run a lot of tests in order to get rid of this part of the curve, and then install the valve hopefully at this point here, where the number of random failures are rather low, and then remove it or change it for a new one some point around here, well before the wear out part of the system kicks in.